Support tickets spiked 300% in an hour because items were randomly disappearing from shopping carts. The team assumed a front-end bug, but the real culprit was eventual consistency in DynamoDB. Two concurrent writes, one adding, one removing an item, were resolved by last writer wins, and the add was silently dropped when the remove arrived later due to network latency. Here's exactly why. Welcome to TheCodeForge. Before we dig into that production issue, let's cover consistency models. A consistency model defines how and when updates become visible to readers. It's the contract that determines whether you see the latest data or a stale copy. The trade-off is between speed and correctness. The CAP theorem says you can't have all three. Since network partitions happen, you choose between CP, consistency plus partition tolerance, and AP, availability plus partition tolerance. Most databases default to AP. Here's how you choose per request in DynamoDB. Strong read forces a read from the leader, ensuring the latest write. Eventual read may return stale data, but is faster. Strong consistency means after a write completes, every subsequent read returns that write. This is achieved through consensus algorithms like Raft. The cost is latency and availability during partitions. In a Raft-based system, the leader waits for a majority acknowledgement before committing. If a follower is partitioned, the write times out, making the system unavailable. Eventual consistency means replicas will converge if no new writes happen, but there's no guarantee when. It's the default in Cassandra and DynamoDB because it maximizes availability. With consistency 1, writes and reads hit a single replica. Fast but may read stale data. For critical data, use quorum to ensure consistency. Causal consistency ensures that causally related operations are seen in order. If a user posts a comment then likes it, all replicas see the comment before the like. Unrelated operations can be reordered. Each operation carries a vector clock. If a replica receives a later operation before its dependency, it buffers it until the dependency arrives. This ensures causal order. Read your writes guarantees that after a user writes, their subsequent reads see that write. This is the minimum acceptable model for any user-facing app to avoid confusion. The client tracks the timestamp of its last write and reads from a replica that has seen that timestamp. In MongoDB, use read concern majority to achieve this. A well-designed system uses different consistency models for different data. For an e-commerce platform, product catalog uses eventual, cart uses read your writes, order placement, and inventory use strong. Here's how you mix consistency levels in code. Inventory checks use quorum for strong consistency, cart uses local quorum for read your writes, and recommendations use one for eventual. Strong consistency is expensive. Use it only for critical data. For non-critical data like logs or recommendations, eventual is fine. The decision tree helps choose. This decision tree helps you choose the right model based on data criticality and throughput. Start with strong for writes and eventual for reads, then optimize. This is the same issue we highlighted at the start. Here's exactly why that happened. The cart service used eventual consistency. Two concurrent writes, one adding, one removing an item, were resolved by last writer wins, silently dropping the add because the remove arrived later due to network latency. The fix was to use conditional updates with version numbers, optimistic locking, and strong reads with consistent read equals true in DynamoDB. This ensures that conflicting writes are detected and retried, not silently dropped. Never use eventual consistency for data representing user intent, carts, orders, balances. Concurrent writes can cause last writer wins to drop data silently. Using eventual consistency for cart writes allowed last writer wins to drop data. Always use conditional updates for user intent data. If your write uses eventual consistency and your read uses strong, you might read a value that doesn't exist yet. Always ensure write consistency is at least as strong as read consistency for critical paths. Reading inventory with eventual consistency can cause overselling. Two users might both see one item left and both place orders, but only one exists. Always use strong consistency for decision-critical reads. The article's DynamoDB code uses the legacy getItemRequest with consistent read. In the Amazon Web Services Software Development Kit v2 for Java, the API changed. Use consistent read in the request builder. For example, getItemRequest, builder, consistent read, true, build. The v1 Software Development Kit is still supported but not recommended for new projects. The article mentions session tokens for read-your-writes but doesn't show code. Here's a concrete example using DynamoDB's consistent read per request, which ensures the writer sees their own writes without needing sticky sessions. The article's debug guide mentions clock skew, but doesn't emphasize its impact on consistency. In systems using last writer wins, LWW, with timestamps, clock skew can cause stale writes to be accepted as newer, leading to data loss. Always run NTP and monitor clock drift. A skew of even a few seconds can cause hard-to-debug inconsistencies. To debug stale reads, check the red consistency level and switch to strong. For write conflicts, look for conditional check failed exceptions and implement retry logic with exponential backoff. Let's run through some common interview questions. How does Cassandra handle read after write consistency? Uses read repair with quorum, but LWW can cause data loss. Use lightweight transactions. When choose eventual over strong, non-critical data, high availability needed, global deployments. What happens with eventual for shopping cart? LWW drops writes, use conditional updates. And a few frequently asked questions. What's the difference between strong and eventual? Strong returns latest write. Eventual may return stale data but converges. When should I use eventual consistency? Non-critical data like social feeds, recommendations, analytics. How to implement read-your-writes. Use session tokens or sticky sessions to route reads to a replica with the user's writes. To recap, consistency models range from strong to eventual. Always use read-your-writes for user-facing apps. Never use eventual for data representing user intent. Mixing models is powerful but requires careful design. Ready to go deeper? Up next, PACELC theorem, then vector and Lamport clocks, then heartbeats and failure detection. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.